Okay, we're in chapter 10. This is part 2. We've gone through the mechanism of our free radical halogenation, and now we're going to talk a little bit about selectivity and bromination. Halogenation, thermodynamics, and kinetics are important for figuring out mechanism. We are not going to focus on this section, so I am going to just slide us through section 4. What I do want to talk about, however, is section 5 with regioselectivity. Now, you are going to see some selectivity when it comes to some selectivity for chlorination, and you're going to see even more for bromination. Right? And it has to do with the intermediates that form. Now, what we looked at was halogenating methane, so there's only one place for the halogen to go. But when we look at more interesting alkanes, right? So we have different options now. You are going to see that the chlorine could add to the 2 position or to the 1 position. But when we look at the breakdown, you do get a slight preference here for the 2-chloropropane. And it's all based on that intermediate, right? So during this mechanism, you have a radical intermediate, right? So something that drove some of the reactions we learned in chapter 8 and 9 was stability of carbocations, right? Well, stability of radical intermediates is going to play a role in predicting major products. Now, chlorine's okay. You do get a major versus minor product, but you still get quite a bit of that primary carbocation. Primary alkyl chloride. However, when you switch this up to bromination is a slower reaction, so it's going to actually wind up giving you a much more selective reaction. That's why you're going to see brominations over chlorinations moving forward, is because it's more predictable. You're not going to get as big a mixture, right? So we're going to find that bromination, right, is a little bit better or more favorable than chlorination. It doesn't tend to add as many times because it's slow, and it's going to give you more selectivity. Making mixtures of products can be a problem. It has to do with the Hammond postulate. That's come up here and there in Gen Chem and organic. All the Hammond postulate tells you is that the transition state is going to look more like whatever it's closer in energy to. So your transition state for chlorination is going to be more similar than reactants because energetically it's closer to the reactants, whereas the intermediates in the bromination are closer in energy to that transition state. So you don't need to be able to regurgitate that, but that's what that slide is about. Right, it's a picture of the transition state. We'll really get into that here. When you look at these energy diagrams for chlorination, right, the energy difference between that highest point where the transition state is, it's just a lot closer together for chlorination. So the likelihood that you could get over one hump, it's not that much different to get over the next one. But for bromination, there's a significant difference, right? And so you are going to get increased selectivity there. All right, you start adding in a tertiary position, right? There's a hydrogen right there. It's going to be a little bit more selective for chlorine, but not much. We went to 65-35 over 60-40. But by the time we go with bromination, you are only making that more substituted alkyl bromide, right? It's happening 16 times faster, right? Or not faster, more often. And so you're getting a negligible amount of that primary alkyl halide. And this is just comparing the selectivity of different halogens. Fluorine, almost no difference. So you would get a lot of all of the possibilities depending on what you're adding the fluorine to. Chlorine, you do get preference for tertiary, but the difference between these two isn't huge, so you would likely get a mixture. Then, of course, by the time you hit bromine, right, you're getting much preferred regioselective, what's the word? Halogenation to that more substitutive part. We won't worry really with stereochemistry because if you make a new chiral center, you're going to make both R and S, and it has to do with the shape of that radical intermediate. It's not quite a carbocation, but it's not going to be hindered like a carbanion would be, right? It's kind of flat-ish, so you can react on either side. A racemic mixture will be obtained. We're just going to say that over and over again. All right, now something that we need to talk about is what to do if you have another functional group that is going to be sensitive, right? So, for instance, if you took an alkene and you reacted it with Br2 and light, well, the bromination is going to be kind of, the free radical bromination is slower. So you're going to get competition, right, with making your dialkyl halide. But what if we want to add bromine, right, to replace one of the hydrogens? How can we do this? Well, if we can't introduce Br2, we just can't, right? Because if we introduce Br2, it's going to compete with the double bond reaction, that addition reaction. So we have to be creative, right? It will be selective for the allylic position, and we'll talk about that in just a moment. But since I started this conversation about the reagent, let's continue there, right? So to avoid side reactions with Br2, you can use NBS. Now, you guys saw that in the lab that we did, or that you did virtually. NBS is essentially just kind of tying the Br2 up so that you don't have a bunch of Br2 running around that could react with your double bond. And so it can be initiated with light, just like Br2, and it can produce bromine radicals, which can then go on to those propagation steps. So using NBS and light works the same way as Br2. It just does not mess with your double bond. Now, where is it going to go? That's where this is important. There are really two places that bromine could go. It is not going to add to an sp2 carbon. So will not add here. It's not going to happen. It's going to be on an sp3 carbon. So we have two choices, right? We can add, no, that's not what we meant to do. We can either add to one of the CH2s across from the double bond or one of the CH2s next to the double bond. The more reactive spot is going to be that CH2 next to the double bond because the intermediate will be resonance stabilized. So you are going to get a major product with the bromine on one of the sp3 carbons, but the one next to the double bond, right? Because anytime you can stabilize that intermediate, it's going to lower the activation energy. The propagation steps look exactly the same, right? The only thing that's different is initiation, right? The initiation step is cleaving the NBR bond. But then it goes on to the first propagation step, the second propagation step. You would still have termination steps as well. So you see MBS is really useful here. There is potential for rearrangements. I don't want you to worry about that. I'm not going to ask you about this portion. Now, there are some interesting little topics in this chapter, but we are going, I recommend reading them. I think they're interesting, but I'm not going to test you over them. Look at the radical reaction for atmospheric oxygen. It's really interesting about why we don't use chlorofluorocarbons anymore. Okay, so we're going to take just a brief moment to talk about autooxidation. This is just important if you're ever working in a lab. If you have something called peroxides around, there are certain kinds of compounds that can oxidize, react with O2, and that you do not need to know this mechanism here. It can make something that is not safe, right? Hydroperoxides, if you've got ethers around, they can auto-oxidize. Anytime you buy diethyl ether, you've got to use it within like 6 months to a year, or you have to get rid of it because it can form these explosive compounds. Now, you're going to notice lots of chemicals come in dark containers. It's to prevent the light from coming in and reacting with them and accelerating these reactions with O2. Amber bottles are good for that. Some reagents even come in completely opaque brown bottles. We touched on this in the first video. These oxidizing reactions, these auto-oxidations, they can be a problem in a chemistry lab and storing chemicals. They can also be a problem in aging, right? Things like triglycerides can auto-oxidize, and this kind of thing. And when I say aging, I'm talking about the aging of things like food. That pesky aging avocado situation. It's because O2 is reacting with the fats, and you're getting these little changes in the chemical structure, and that's what's going to cause food to become rancid and toxic. That's why preservatives are often used. Preservatives are things that are fighting against that auto-oxidation. So something that can stabilize those radicals that are formed, right? And there's just some pictures there. Vitamin E, vitamin C, these are antioxidants. They are going to fight that auto-oxidation process by reacting with the O2 radicals. I'm just going to continue on because this is going to be the last video for this chapter, because there is only one other mechanism that you need to know, and it's not even for a new reaction, right? So when you do the anti-mark addition of HBr to a double bond, right? So we can take this asymmetric double bond. We know that if we treat with HBr and peroxides, that we can add that bromine to the less substituted side. We skipped that mechanism in chapter 8 because it is a radical mechanism. So hello, this is the radical mechanism chapter. So there are going to be two mechanisms you're responsible for in this chapter. You're going to be responsible for the mechanism of the free radical halogenation of an alkane and of the anti-Markovnikov addition of HBr. Now, let's get started. Initiation. Now, this one is a little bit different. This initiation has 2 steps. This is initiated because of the peroxide you have. This OO bond is sensitive to initiation. You can use heat. Sometimes light might pop up, but heat is usually what I see here. And it is going to cause that homolytic cleavage, right, of your oxygen-oxygen bond. And so, I don't know why I draw two. You're going to have two RO radicals. Now, it is that RO radical that reacts with HBr. This is still considered an initiation step because this is not a starting material. This is a catalyst that jumpstarts the reaction. This is going to cause another homolytic cleavage where we wind up with some alcohol and bromine radicals. That bromine radical is what's going to move on to our propagation step. When you have a double bond, and let's go ahead and just use the one I'm used to doing here, and you have a bromine radical, you are going to add the bromine first, whereas when you just add HBr, the H adds first. So this is why we wind up getting the placement of the bromine that we do, is because it goes on first. And it's going to go to the less substituted side so that the radical that is left behind is the most stable one possible. If the bromine went to the more substituted side, we would have a primary radical instead of a secondary radical, right? So it's all about stability of that intermediate. Then once we have our carbon radical, then it is just, remember this is propagation, it's going to be something that can react with the HBr. So we'll put that proton, or not proton, we'll put that hydrogen on, and there's your neutral product. But it's also going to make some bromine radical. So that bromine radical can just keep propagating more and more reactions. Now, they don't even show you all of the possible terminations, but there are several, right? A termination can happen with any of the radicals that were formed, but bromine radicals are formed in multiple steps. So it's just the most likely one you're going to see, right, where you form a little bit of Br2. But you also might see a bromine radical and an RO radical, and then that would be a termination step also. Not a super likely one, but it's really any two radicals that could come together, right? So there are a few more that you could make. And that is it. That's all from chapter 10 that I am going to expect you to know for this exam. You do not need to look at the thermodynamics, the stereochemistry, just you can make multiples. We are going to skip polymerization. Such a long. And what I want to leave you with, because we've touched on it in the past, is synthetic utility. One of the nicest things about this reaction is it is the free radical halogenation, is that this is the only reaction that you have with an alkane. So if I give you an alkane, any old alkane, and you have to start a multi-step synthesis with it, you should say, thank you, I know the first reaction because this is the only reaction I know. It will be important for you at that point to say, okay, I know that's what I want. It doesn't really matter, where I want it to add. It is going to add to the more substituted spot. Now, if I wanted the bromine to be elsewhere, now I can move it. We learned about that in chapter 8. This is a big stepping stone to next week's dive into synthesis. So make sure that you are taking in some of these patterns. I am not going to go through all of these slides, but Klein does an excellent job of summarizing reactions for you and giving you strategy for working problems. But that's it. I should probably stop talking now. I will see you guys later.